Thank you, and thank you for having me here today. So I think it's safe to say that we want more data on the habitability of planets around other stars, and that we eventually want to search such planets for signs of life. I'm going to talk today about one mission that is being studied by NASA in advance of the next astrophysics Decadal Survey in the United States that has the goal of doing that. But before I get there, let me just, for the folks that are in the astrobiology audience that may not be familiar with the Decadal Survey process, every 10 years, the astrophysics community here in the United States prioritizes the science that they think should be driving the following decade of things done by NASA and by NSF, and I believe by the Department of Energy as well, in the field of astronomy and astrophysics. And exoplanets and habitable exoplanets is under the purview of the astrophysics Decadal surveys. And so the missions that would be studied in advance of that would be the ones that would be up for consideration for the next decade's worth of missions. That's also important for the time scale, because any of the missions that would be prioritized in the Decadal Survey probably wouldn't start building them until 2025, till the mid-2020s, and they probably would not launch until the 2030s. So this is stuff that we're thinking about far in the future, but the time is now to start prioritizing them. And I'm not going to suggest what all of you should do in terms of what types of papers or what you should promote in the Decadal Survey. But if you're interested in the search for life, and if you're interested in the search for habitable planets, I think as a community of astrobiologists, it behooves us to be involved in that process as it occurs. So without further ado, this is HabEx. This is one of the four. Here's the HabEx team. I'll note that there are astrobiologists, bona fide astrobiologists with degrees as such on the team, and people that are well published in the astrobiology literature. Ty's not in this picture, but because I think he wasn't at the particular face-to-face meeting. We also have Leslie Rogers and Sarah Seegers, one of our co-chairs. They've all been publishing astrobiology stuff. So the goals of the Havok Study are to develop an optimal mission concept for characterizing the nearest planetary systems and detecting and characterizing a handful of exoearths. So this is, I'll get into this in a minute, but this is unlike LUVOIR, which is trying to get a statistical sampling of exoearths or potential exoearths. Havok's goal is basically how big do we have to be before we can get a few of them. And then given that optimal concept, maximize the general astrophysics science potential without sacrificing the primary exoplanet science goals. And so what that's saying is we will optimize this for exoplanet science and then find out what kinds of other astrophysics we can do once we've optimized for the exoplanet science case. So it's not just about exoplanets, but it is the main architectural traits are primarily, but not exclusively, driven by exoplanets. So if you've heard about LUVOIR, which stands for the Large UV Optical Infrared Mission, that's another thing that's being studied in advance of the Astrophysics Decadal Survey that would have a very similar science case. It's looking for habitable worlds. It's going to try to characterize them spectroscopically. It's also going to do a lot of general astrophysics. We get the question, what's the difference between the two? Well, they have a slight difference in how they're balancing their primary science goals, but they have the same primary science goals. They're both going to do habitable exoplanets and biosignatures and a broad range of general astrophysics. The two architectures will be different in focus, as I mentioned before, whereas LUVOIR is kind of balanced between exoplanet habitability searches and astrophysics. HabEx is defined by optimizing for the exoplanet science case first and then doing the best we can given that optimization for the rest of astrophysics. And there's also different levels of ambition between the two missions. LUVOIR is trying to be big and ambitious, and HabEx is trying to be more cost-constrained and less technically risky. So the analogy I give here is like, and I apologize to the vegetarians in the room, I just don't have the right analogy for this for a vegetarian menu, but you can think of it as like the slider. You know, there's going to be 4 architectures studied between the two missions. You can think about the slider, the cheeseburger, you know, the sirloin steak, and like the filet mignon. And if Dr. Grunsfeld has his way and we assemble something in space, that'd be the prime rib at the top of the menu. And the goal really here is that continuum is intentional strategically. As an exoplanet scientist, I'm happy that we're going to have a range of options presented to the Decadal Survey, because Decadal surveys are unpredictable in how they're going to operate. We're talking about a large sample size of past Decadal surveys, and we're talking about predicting the actions of a few humans. I think the news over the last couple of years has shown us that predicting the behavior of large groups of humans is hard enough. Predicting the behavior of small groups of humans is even more difficult. And I think it's wise for us to have multiple options going into that kind of scenario. So if all that was just NASA speak, just take this away from it. The goal of the Highback Study is to find out what a smaller scale NASA-led mission looked like if it was specifically designed to hunt for planets around our nearest stellar neighbors. So that brings us to the science cases, and I've gone over these a few times, so I won't go over them into detail now, but it's habitable exoplanets, exploring in detail our nearest planetary systems beyond just the habitable worlds, and then the broad range of astrophysics. And so a lot of that's driven by looking for this pale blue dot, and I think people in this audience are familiar with this concept of not just characterizing it on its blueness as a color, but spectroscopically, in addition to the blue, what molecular absorption features does it have? Does it have a red edge? Does it have carbon dioxide, oxygen, methane, water vapor, and so on? And so these are some simulations by Kat Fung, who's, I believe, going to be speaking later in this session, and Ty Robinson, who I believe is also going to be speaking later in this session, that shows what we could do. I believe this is a 200-hour integration time on a fairly nearby Earth-like world. And this shows you that we can, in fact, we think, resolve some very important features like water and ozone and oxygen. We are going to try to go out past 1 micron here. So this is a simulated spectrum from 0.3 to 1 microns. We're going to try to go out past 1 micron, but it's going to be sort of a best effort. The mission won't be designed from the ground up to be optimized to operating past 1 micron, and we'll do sort of the best we can given the technologies we have at the time. We're also worried about the false positives. This is the part of the mission or the study that's the most near and dear to my heart. I don't want to spend a large amount of taxpayer money and the entirety of my career and most of many other people's careers, and then call the president and say we found signs of life, and then have a bunch of papers in the literature a week later saying, no, you found interesting photochemistry. That's not what I'm dedicating my life to. So we want to know about those potential false positives that could trip us up in advance, and we're incorporating that into the types of things we want to look for. This is not a Habek's formal slide. This is something that just is my own brainchild of how we might do an observational run on a particular planet. Starting with finding out if there's too much dust in the exoplanet system, and if there is, we'd get a picture of that dust because there's science there, and then we'd move on to our next target. If there wasn't too much dust to cloud out the planets, we would start to look for planets. If it had planets, great. And actually, to be honest, if it had planets, we wouldn't know what planets they were at first. We'd have to revisit multiple times to define the orbits and maybe get some colors as a preliminary characterization scheme. But eventually, we would determine whether or not any of those planets were rocky and in the habitable zone. We'd get a low-res spectrum of those rocky worlds, find out if they had water. And we look at water first because it's got whopping big absorption features that should be relatively easy to detect. If it had water, we'd start to get excited. We'd look for oxygen at a higher, a medium or medium to high spectral resolution of around 150. If we found the oxygen, now we're starting to get really excited, but now I'm starting to sweat about those false positives for life. We'd get a long wave spectrum if we could. Well, first of all, we try to quantify the oxygen. If it has too much, that's bad news for a reason I don't have time to go into detail on, which is a false positive indicator. But if it didn't have too much oxygen, we'd look at the long wave spectrum. We'd look for methane, which is the great pair to have with oxygen. If we found the methane, that's when, well, honestly, we'd probably be cracking open champagne bottles like after every one of these steps, but that's the one where I'd probably open the bottle of champagne and then take it down to, I don't know, the Bahamas or something and start planning my retirement. Because that's when I would be comfortable putting my name on a paper saying we found signs of life on an exoplanet, at least me personally. As to whether or not that applies to you, that's up to you. Now, as we're doing all this, we're going to also be able to observe other kinds of planets, a diversity of worlds in that system. So even though we're looking for Earths, the way that the instrumentation is set up, we'll also be seeing other pale dots that may not be blue, and they may not be quite as small as Earth. And we're going to get Jupiters at a range of distances. We're going to get Neptunes and these weird super-Earth sub-Neptune things, and we're going to get spectra on those things too. And so even if you aren't convinced that the search for Earths is what we should put all our chips in, and we should be thinking about comparative planetology, HabEx is going to do that as well. And the other way to think about this is HabEx is really designed to do all this science in our local system. It's not the mission that's going to do a survey of everyone, to put another analogy out there, it's not the thing that's going to do the survey of everybody in the United States. It's the thing that's going to knock on doors of a few neighbors and find out what they're thinking. Because HabEx is really designed just to look for these kinds of planets and do this kind of science in our nearest stellar neighbors. So we are going to do some general astrophysics as well, and because this is a habitability session, I'm not going to go into it. But a lot of this is astrobiology too, because one thing that I love about astrobiology, it's not just about the search for life, it's about sort of the history of life and the history of astrophysical and cosmological conditions that led to the origin of life on Earth. And we'll learn a lot about how stars form and how planet systems form and how galaxies form and evolve over time with a HabEx or LUVOIR-like mission. And we'll also do some cool planetary science astrobiology. We'd be able to get better resolution on, for example, geysers from Europa. Are we coming up on my time here? Okay. So this is just for scale. We have Hubble on the left. HabEx is going to be looking at 2 sizes. We've already looked at a 4 meter, which I'll talk about in a moment. And we're also going to be talking about a 6.5 meter version of HabEx in the future. We haven't considered that in detail quite yet, but this gives you a sense of how large something like this might be. The 6.5 meter would borrow from JWST, so this would be somewhere in size for the 4 meter version between Hubble and Webb. Now, this is not an eye chart. I don't expect you to read it. This is how we made decisions on what kinds of starlight suppression technology and major architectures we would use to find these habitable exoplanets. It's a difficult engineering problem, and we had 4 major choices we were considering as a team. We could have used a coronagraph, which blocks light inside the path of the telescope from the star, so you can see the Earth-like worlds. We considered a star shade, which blocks the light before it hits the telescope. There's some difficulty in making the star shade itself, but if you can make a star shade, you can use a dumber telescope, to put it simply, to find your planets. Then we considered something with 2 star shades. We'd use 1 star shade to search for planets, because the problem with the star shade is it slews, and as it's slewing, you can't search for exoplanets. So we'd have 1 star shade finding planets while another one was slewing maybe to your next target, or slewing to that target to do characterization of it. And we considered a mission with 1 star shade and 1 coronagraph. And there's some advantages to that, which I'll get to in a minute. Now, what we did was we had a series of musts that the mission had to meet, a series of wants that we wanted it to meet, a series of risks to the mission, and a series of opportunities to the mission. And the colors from blue, green, yellow, red are from best to worst for each of the 4 architectures we were considering. This is how we made the decision. You can see us like we had data on the left and the trade matrix on the right, filling this in as we went along 3 grueling days. The thing that really drove our decision in the end was the science return, and the best science return came from the combination of the coronagraph and the star shade, so that's what we're going to go forward with. That's news. We just decided this on Friday in Boston. And so we're going to, the first architecture for HabEx will be a 4 meter monolith with both an internal coronagraph and an external star shade. And that's nice because they're complementary. Coronagraphs are nimble, while star shades can do deep, broad observations spectroscopically. Now, that does mean we're going to carry more technological challenges with us. The thing we're going to do there is we're going to talk about D-scopes if we have to. So that's where I'm going to close to take questions about this. But I'd like everyone to just think about the astrophysics future that they want and to participate in the activities that are going to determine that. Thank you for your time.
We have time for 1, maybe 2 questions if you're quick.
Could you, oh, do we have someone walking up? Never mind, go ahead.
Thanks, Eric, that was generous. Yeah, no, I just wanted to say, that was a great talk. I just wanted to say that when I think about the difference between LUVOIR and HabEx, I do just like to re-emphasize the point that you made. These, we're doing deep dives into our neighboring systems and finding out like whatever is there, including the habitable planets, but there's so many other kinds of planets that'll be in that same discovery space that getting to know our neighbors really well is a major focus for this concept, which I think is super exciting personally, even more so than the big survey.
Yep, thanks, Maggie. Totally agree. And I should point out, when I showed the photo, we have another astrobiologist on the STDT, which is Maggie Turnbull, who just asked that question.
Okay, well, let's give Shawn another round of applause. Do you have a quick question?
Yeah. Hey,
Okay.
Shawn, have you guys also thought about a broader general observer program, or is that just in the future you're too concerned with just meeting the requirements?
So one of the trades we were looking at is the amount of guaranteed general astrophysics / guest observer time that the different architectures would enable. The star shade only missions, or the 2 star shade missions, had the most there, because while those star shades are slewing, you're guaranteed guest observer time to do other kinds of science. But that's a guarantee. That's like, if all us exoplanet scientists are super greedy, there's an upper limit to the starshade-driven missions, to the amount of time we could even like try to get. That doesn't mean that the coronagraph missions, with the coronagraph and a starshade or the coronagraph only, couldn't also decide in the future to have a similar amount of guest observer science. So how much guest observer science there is really a decision that would be made by a future astrophysics community. I personally think more is better. That's related to our architectures to the extent that certain architectures guarantee a floor.
And would that be guaranteed also by having?
Sorry, we're going to have to cut the
Yeah,
questions and
I can
move
answer
on.
more about that later. Yep.
All right, let's give Shawn another round
Thank
of
you.
applause.